we can start. Okay, do everybody see the lecture note? Everybody see it? Is it good? Okay, so you see the lecture note? Okay, so let me see. Just a moment. Okay, so okay, so everybody sees the lecture note. Okay, so that's good. Okay, so you see the lecture note. Okay, so let's start the lecture. Okay, so we've been talking about the impulse functions from last lecture. Okay, so the impulse functions. Okay, so the impulse functions are right. So we've been talking about the impulse functions, right? So do everybody see the note? What I'm writing here is, can you see me? The writing? Okay, so that's good. Okay, so that's good. Okay, so the impulse functions, right? So the impulse functions are what we have been, okay, so I've been talking about on last Friday's lecture, right? So you started from the D, okay, so you started from the D tau of t, right? So the d tau of t is such a function that has been, okay, so that has been from minus tau to tau with a unit impulse, right? So with a unit impulse, so the heat is 1/2 tau, so that's the heat, right? So the d tau of t is equal to 0 if t is less than minus tau or t is greater than tau, and it is equal to 1/2 tau if minus tau less or equal than t less or equal than tau, right? So we're considering this function. Now the important property of this function, okay, so the important property of this function lies in the fact, okay, so it lies in the fact that the integral, okay, so the integral from minus infinity plus infinity of d tau of t dt is just equal to 1, right? So this is kind of used to model the behavior, okay, so the behavior of an impulse function, right? So it's used to model the behavior of an impulse function. Okay, so this is kind of the start. Okay, so that's the start of our consideration of impulse functions. And in particular, if we set d tau of t, if tau is going to 0, so you can see that if tau is going to 0, you're going to see the picture like this, right? So what happened here is that you started from minus tau, you end up with tau. So if your tau is this value, this is your function. And if tau is kind of shrinked by a half, you will see this function. If tau is shrinked by 1/4, you are going to see a function like this, etc. So in the end, you are going to see a blow up of your function, right? So this is what we call it the delta function, right? So this is what we call it the delta function. Okay, so that's what we can be talking about, the so-called unit delta function, right? So unit delta function, or sometimes we call it the unit impulse function, right? So sometimes we call it the unit impulse function, right? So what is the unit impulse function? Well, according to our definition, okay, so according to our definition, the unit impulse function is a function that's defined in this way, okay? So it's defined to be 0 except at point 0, and the 0 is infinity, but the infinity integral is equal to what? Any questions? Okay, so the unit delta function is delta of t is equal to 0 if t is not equal to 0. It's infinity if t is equal to 0. But this is not enough. This is not enough for the unit delta, but you have to do the integral from minus infinity to plus infinity of delta t dt. That must be equal to 1, right? So you can see that the unit step function is just such a function, right? So it's just such a function that's kind of have a blow up at point 0. So point 0 except the point 0, it's 0, it's infinity, right? So at point 0, and it's 0 everywhere else, right? So that's kind of the unit impulse function. Now this unit impulse function is used to model kicks, right? So it is used to model some kicks applied to any mechanical system, right? So for example, you can consider a mechanical vibration mu double dot plus gamma of u dot plus k of u is equal to the external forcing, where the external forcing you can take to be F0 delta of t, or maybe F0 delta of t minus t0. If you shift delta up to t minus t0, it means that you are considering an impulse function. So the impulse happens at point t0. Before this time is 0, it suddenly have an impulse and then comes back to 0 again, right? So you consider this type of function. Okay, so the important thing is to consider the Laplace transform on both sides of this equation. So mu double dot plus gamma of u dot plus k of u is equal to Laplace transform of delta of t minus t0, right? So that's you want to apply the Laplace transform to solve this differential equation. That means you have a force, you have a mass subjected to a kick force and a subject to vibration, and you would like to see how this mass is kind of moves under such a force field, right? So that you want to take a Laplace transform of the delta function. So what happened here last time, we've been proving that Laplace transform of delta t minus t0 is equal to what? It is equal to, so the method we used last time is that we just apply the Laplace transform, so e power minus snt delta t minus t0 dt, right? So you apply the Laplace transform method. So what does it gives you? What does it give you? Well, it is going to give you, right? So it is going to give you that this is nothing but, so you have a delta function here. So the delta function, so you can only, what you can do is to consider the limit as tau go to 0 of integral 0 to infinity minus snt d tau of t minus t0 dt. So that's kind of what happened here, is that you can change a variable, right? So let's limit as tau going to 0 of the integral 0 to infinity e power minus s. So I want to replace t minus t0 by dt. So that's kind of, so you can say this is a t tilde, right? So that's t tilde is equal to t minus t0. So t is a t tilde plus t0. So, and if you do that, you are going to end up with e power minus s t0 of the limit as tau going to 0 of the integral from 0 to minus infinity minus s of t tilde d tau of t tilde dt tilde, right? So you get this. Okay, so, and the latter integral was shown to be equal to 1 if you take a limit from last lecture. Okay, so this was shown to be equal to 1. So once this is done, you can see that the Laplace transform of delta of t minus a is equal to e power minus s multiplied by a, right? So this is one of our important results for the Laplace transform that you can find on the table. So it's here, right? So it's on the last line of the table where you have if you have a delta t minus a, it is going to, under Laplace transform, it will be transformed to e power minus a times s, right? So that's kind of the thing. Okay, so this is kind of nice. Okay, so this is kind of nice, and let me look at this once more. Okay, so let me look at this once more. Okay, so now I would like to consider a very general situation. Okay, so I would like to consider a very general situation. Namely, okay, so namely, if you want to have a delta function, right? So if you want to have a delta function that has this property, okay, so I want to say the integral from, okay, so I want to say the integral from minus infinity to plus infinity, okay, so let's say from minus infinity plus infinity of delta t minus t0 multiplied by any function f t dt, right? So how do I analyze this integral? Well, if you want to talk about that integral, you can first change variables, right? So if you change variables, that's minus infinity plus infinity of delta of t f, let's say t tilde. So t tilde is equal to t minus t0. So the t is equal to t tilde plus t0 dt tilde, right? So you have this. Now, once you have this, you can use the same technique as what we did before. So it's the limit as delta tau going to 0 of the integral from minus infinity plus infinity d tau, right? So d tau of t tilde f of t tilde plus t0 dt tilde. So d tau. And what is the d tau? Well, remember, the d tau is nothing but integral from minus tau to plus tau, right? So and 1 over 2 tau, right? So that's the integral f of t tilde plus t0 dt tilde, where the limit as tau going to 0. So what happened here is that you can see that this is nothing but talking about the following function. Okay, so what's this integral? Well, if you're around t0, t tilde is from minus tau to tau. So t tilde is from minus tau to tau. You can consider this. Let's say this is the function f of t. Then you are considering the integral of this function. So the integral is nothing but the area under the graph of the function f, right? So and the area under the graph. Now, once you know the area under the graph, you can see that if you divide, so the width of this shaded area is 2 tau. As tau going to 0, it is going to gradually approach a rectangle, right? So it's going to gradually approach a rectangle here, where the height of the rectangle is f of t0. So the limits will be equal to f of t0. So this is a very general result. Okay, so this is a very general result. And what does this result say? Okay, so the general result, right? So the general result, right? So this is a very general result. It says that the integral from minus infinity plus infinity of ft multiplied by delta of t minus t0 dt is equal to f of t0. How do we understand this result more intuitively? Well, you can understand it very naturally, right? So you can understand it very naturally by thinking about how the function, the integral behaves, right? So you can think about how the integral behaves. It's very simple. So the delta function is just a function that has an impulse at t0. If it has an impulse, so that means the function is like a t0, there will be such an impulse. So the impulse is helping you to read out the values of f at point t0. So that will result in a ft0. So you can think of delta function as a probe, right? So you can think of this delta function as a probe. It always helps you to read out the value of this function. If you do this multiplication, it always helps integrate it, and it always helps you to record the value of the function, right? So it always helps you to record the value of this function, right? So that's kind of a simple thing to see. Okay, so that's kind of a simple thing to see for the delta function. Okay, so for the delta function. Okay, so that's about the delta function. Now I would like to come back to this formula, right? So this is you see this is the last line of our table, right? So the last line of the table, line 20, is going to say that delta of t minus a is transformed to e power minus as. Now I'm going to ask you the following question. Okay, so I'm going to ask you the following question. What happens if, let's say, Laplace transform of delta of t minus a multiplied by another function f of t? So this is kind of important, right? So you have to know how the Laplace transform transforms a delta function multiplied by a given function. This is not given in the table of this formula, right? So it's not given in the table, but it is required to know that. So if you do this, you can do nothing but calculating, right? So it will be the integral from 0, right? So from 0 to infinity, e power minus s and t multiplied by delta of t minus a multiplied by f of t dt, right? So you're going to treat this function. Now, if you treat this function, you can think of this one as another function u, right? So let's say u of t is equal to 0 if t is less than 0, is e power s and t if t is greater or equal to 0. If you have this function, then this can be written as minus infinity to infinity of u of t f of t multiplied by delta t minus a dt. You get this, right? So that means it's very similar to the general result here, but rather you're going to treat ut multiplied by ft as a whole function. So that means you're going to just have u of a and f of a, because as here t0 is replaced by a. So u of a is equal to e power minus s multiplied by a multiplied by f of a. So in the end, you get two such formulas. Okay, so one formula says the Laplace transform of delta of t minus a is e power s multiplied by a. This is what you can see on the table of the Laplace transform. It's what they give you. Okay, so but what is they do not give you is that you have a hidden line here, which says that if this one is multiplied by f of t, you're going to have s multiplied by a multiplied by f of a, right? So this is something that has been missing, right? So this is something that has been missing. If you look carefully at the table of the Laplace transform here, you can see that they have a line 20, right? So line 20 says the delta of t minus a is transformed to e power minus as, but it didn't really tell you what's delta of t minus a multiplied by f of t. Is a good family. Okay, so for example, if you have a differential equation, let's say m u double dot plus gamma of u dot plus ku is, let's say, equal to let me say delta of t minus pi multiplied by cosine t. If you want to do this, solve this differential equation, you want to apply Laplace transform on both sides of this equation. But what's the right-hand side? Delta of t minus pi is e power minus s pi, but you have to place cosine by cosine pi here, so you're not going to have e power minus s pi, you have minus e power minus s pi. It's a good family, right? So this is a very important formula that is sometimes very useful for your upcoming exams. Okay, so they did test this from time to time during their exams. It's just they want, so that's, I'm calling it the hidden line. Okay, so the hidden line 21 on the table of Laplace transforms. Right, so it's a hidden line 21. Okay, so this line is usually not given on any of those exam sheets, right? So they are not going to give you the sheet for this line, but it is very important to realize that you must have this line on the hidden on the table of Laplace transforms in order to perform some of the calculations. Okay, so now for the rest of today's lecture, I'd like to give you some examples that we can see. Okay, so this one is what there was an example we've been talking about last lecture, right? So we find a solution of this initial value problem where the right-hand side is the delta function delta t minus 5. So what we have been doing there, is that first apply Laplace transform on both sides, and remember that delta t minus 5 is transformed to e power minus 5 times s, right? So, and once that is done, you know the Laplace transform of y is equal to e power minus 5 times s multiplied by this function. So you want to transform this function back, right? So you want to transform this function back. So what happens here? Is that you would like to, so it is a good idea. Okay, so it is a good idea. Okay, so whenever you are applying, right? So what happened here is that it tells you the Laplace transform of y, right? So according to this table, right? So according to this transformation. So what does it give you? Okay, so it gives you that, right? So let me make it larger. Okay, so this example says that Laplace transform of y is equal to e power, right? So e power minus 5 times s divided by 1 over, right? So 1 over the 2s squared plus s plus 2, right? So 2s squared plus s plus 2. So you get this. Now, once you want to transform back, okay, so you want to transform back, you have to remember that you're always trying to use the shift table of Laplace transform. So you can see from here that the shift table consists of 2 lines, right? So one is this line 11. Excuse me, any question? Okay, so one is line 11. Okay, so one is line 11, and okay, so the other one is line 16, right? So you have to try, you see, from line 11 to line 16, you have to kind of tell yourself what is small f and what is capital F. Okay, so what happened here is that this one is going to serve as your capital F of s, right? So remember, if you have an exponential shift, c and multiplied by s, f of s, this must correspond to what? It must correspond to a forward shift f of t minus c, right? So that's, but if you do an usual shift on the image, then it's going to be exponential of cs, right? So exponential, let me use a here, okay, so a of t multiplied by f of t. So you have 2 ways of doing this transformation. So you want to have this one as your capital F of s. So what you want to do is that if you have f of s, then under the inverse Laplace transform or on Laplace transform, it must be corresponding to some f of t. So if f of s is 1 over 2s squared plus s plus 2, and you can find your small f of t simply by partial fractions. Okay, so the partial fractions is going to tell you that f of t is equal to, so after this partial fraction analysis, it is going to tell you that f of t is equal to, okay, so it is equal to this function, right? So that's 2 over square root of 15, right? So e power minus t over 4. So the f of t is 2 over square root of 15, e power minus t over 4, multiplied by, right? So multiplied by sinuses of square root of 15 over 4 of t, square root of 15 over 4 of t. You have this. So if you have this, you can apply this formula, but remember you must use ft minus c. So that's y is equal to the inverse Laplace transform e power minus 5 times s, the capital F of s, as equal to f of t minus 5. And if you want t minus 5, I mean multiply by ut minus c, right? So I forgot this. So as ut minus 5. So that means you're going to have ut minus 5. ft minus 5 is 2 over square root of 15, e power minus t minus 5 over 4 sinuses of square root of 15 over 4 multiplied by t minus 5. So this is how you get a solution for a differential equation with an impulse right hand side. So this is kind of typical example. This is typical example. For today's lecture, we still have about 25 minutes, half of today's lecture. We're going to practice one more example. Okay, so we're going to just practice one more example. But before I do that, I would like to tell you that here by the end of the lecture notes, I have listed quite many examples for you to practice. Okay, so there are 13 such exercises for you to practice. So for the rest of today's lecture, let's try this example. Okay, so the example says y double prime plus 2y prime minus 3y is equal to delta t minus 3. Okay, so y double prime plus 2y prime minus 3y is equal to delta of t minus 3 with the initial conditions y of 0 is equal to and y prime 0 is equal to. So let's look at this example. Okay, so y plus 2y prime minus 3y delta t 0 and 1. Okay, so the initial conditions are 0 and 1, right? So let's try to solve
such a differential equation. Okay, so let's try to solve such a differential equation. How are we going to do it? Well, we're going to apply the Laplace transform on both sides. Y double prime plus 2y prime minus 3y is equal to Laplace transform of delta of t minus 3, right? So that's what you want to do. As always, the first step is to apply Laplace transform on both sides of this equation. Now, once Laplace transform is applied, you have to apply the formula Laplace transform of y double derivative is equal to s squared Laplace transform of y minus s of y of 0 minus y prime of 0, right? So, and y of 0 is 0, y prime of 0 is 1. So that's s squared Laplace transform of y minus 1, right? That's the transformation. And Laplace transform of y prime is equal to same thing, Laplace transform of y minus y of 0. y0 is 0, so s Laplace transform of y. And so therefore, you can see the left-hand side, right? So the left-hand side now becomes s squared Laplace transform of y minus 1, right? So minus 1. And plus the linearity tells you that 2 Laplace transform of y prime is Laplace transform of y minus 3 the Laplace transform of y. This one is equal to, so if you calculate, it is equal to s squared plus 2 times s minus 3 multiplied by the Laplace transform of y minus 1 is equal to Laplace transform of delta t minus 3 is equal to what? Well, you can look at the table, but if you remember, we just mentioned it. It's minus 3 times s, right? So minus a of s. So it's an e by minus 3 times s. So that's what you can get from the Laplace transforms. And indeed, it is so, right? So e power minus 3 of s. So that's kind of the thing, right? So you get the Laplace transform of y is equal to 1 over s squared plus 2s minus 3 plus e power 3s, 1 over s squared plus 2s minus 3, right? So that's in the end, you get the result, right? So you get the result that Laplace transform of y, just according to with the previous table, it will be equal to this 1 plus e power minus 3s, right? So 1 plus e power minus 3s divided by the numerator is s squared plus 2s minus 3. So s squared plus 2s minus 3. So you can split it into 1 over s squared plus 2s minus 3 plus e power minus 3s 1 over s squared plus 2s minus 3, right? So you get something like this. Now, as long as you obtain something like this, you can see that if I set, okay, so you can still use this table of Laplace transforms, right? So what happened here? Is that if you set, right? So if you set capital F, so what happened here is that if you set capital F of s is equal to 1 over s squared plus 2s minus 3, then you would like to apply an inverse Laplace transform. You would like to apply an inverse Laplace transform, right? So you would like to apply an inverse Laplace transform. So what happened here is that you apply an inverse Laplace transform. It will going to be transformed to small f of t. Now, once you have that, this one, okay, so this e power minus 3 times s is multiplied by f of s. You have to use the shift table of the inverse Laplace transform. It is going to be giving you ut minus 3 multiplied by small ft minus 3. You have to shift this table from Laplace transform. This, for all this stuff, they're not kind of so hard, because if you don't know them, you can search for this kind of transformations on the table. Here I'm using line 16 of the table, right? So so you can always resort to the tables to obtain what you want, right? So that's kind of the thing. So the only thing that's known, the only thing that's unknown is about f of t. So that means you would like to consider the inverse Laplace transform of the function s squared plus 2s minus 3. Is that good for everybody, right? So how do we find the inverse Laplace transform of this function? Well, as I told you many times, if you look at the denominator, you have to just determine whether or not you would like to factorize the denominator or you would like to complete the square. Here, obviously, you should factorize the denominator. So that means this is going to give you inverse Laplace transform of 1 over s plus 3 multiplied by s minus 1. So that's the inverse Laplace transform. So therefore, you just want to just check that s plus 3 multiplied by s minus 1 is kind of partial fraction decomposition into a over s plus 3, b over s minus 1. So that's going to tell you that this is s plus 3 of s minus 1 multiplied by a of s minus 1 plus b of s plus 3. So that's going to tell you that this is a plus b multiplied by s plus 3b minus a, right? So divided by s plus 3 multiplied by s minus 1. So that means you're going to tell me a plus b is equal to 0 and 3b minus a is equal to 1. So that's going to tell you that you sum these two, so b is equal to 1/4, right? So and a is equal to minus 1/4, right? So that's the transformation. Okay, so that's the partial fraction decomposition, right? So you have the partial fraction decomposition. So with this partial fraction decomposition at hand, you can see that this is nothing but the inverse Laplace transform of minus 1/4 of s plus 3 plus 1/4 of s minus 1. So that's the inverse Laplace transform. And then you should look at the table again, right? So the table tells you that if you want to transform s minus a, you want to transform back to e power at. So in the end, the result is minus 1/4 e power minus 3t plus 1/4 e power of t. So that's the inverse Laplace transform of f, which is just your function here. Is a good parabolic, right? So that's therefore you can always use this function as your f of t. You transform into here, right? So that's what you want to do in this whole business, right? So and it's indeed not so hard to practice, right? So it's indeed not so hard to practice. Okay, so that means that we are going to. So let me summarize this result. It's saying that the result is saying that the Laplace transform, so the y is the inverse Laplace transform of our capital F of s plus, right? So plus the inverse Laplace transform, right? So of e power minus 3 times s capital F of s, right? So it's the transformation both these functions, but the inverse Laplace transform of capital F of s is small f of t. Small f of t is equal to small f of t plus this u of t minus 3 multiplied by small f t minus 3, where the capital F of s, as we calculated, it was s squared plus 2s minus 3, right? So, and therefore, the small f of t was found, right? Was found by partial fraction decomposition to be minus 1/4 e power minus 3t plus 1/4 e power of t. E power of t. You have this function, small f of t. So that means the y function is found. So it is 1/4 e power minus 3t plus 1/4 e power 3t, right? So plus u of t minus 3. And then you have to replace everything, all the t by minus 3, t minus 3, and then plus 1/4 e power t minus 3. So you have to replace all the t by t minus 3 in order to reach a satisfactory answer. Okay, so that's how you kind of, the whole process is kind of how you solve a differential equation like this, right? So how you solve a differential equation like this, you can see that you just, it's just a kind of makes a very synthetic use of all the techniques that we have been learning so far, right? So all the techniques that we have been learning so far. So this is kind of not so simple, right? So that's at this stage of the class, everything is very synthetic, and it is required. You're required to grasp about, I mean, in a very synthetic way, everything around the Laplace transform table, as well as the corresponding transformations. Okay, so I've shown you here many different exercises that helps you to understand what is going on in these lectures. Okay, so now for the rest of today's lecture, okay, so I'd like to, we would like to come back a little bit. Okay, so there was one example I would like to re-emphasize about the lecture, right? So I was want to re-emphasize about the lecture. Okay, so So that's one example I would like to re-emphasize is the one I talked about before, right? So it's one of them I talked about before. I talked about it quickly. Okay, so but I think it is worth looking at the problem again and try to see what kind of techniques are there behind this scene. Okay, so this one says, can you solve the initial value problem? 2y double prime plus y prime plus 2y is equal to g of t, where y of 0 is 0 and y prime of 0 is 0, where g of t is equal to 1 if t is between 5 and 20 and 0 otherwise, right? So you have this. Now, if you want to play around the first important thing, okay, so this is also typical for your exams, is that the first important thing is that you should turn your function g of t in a right way onto a sum of unit step function. So for here, you see the t is between 5 and 20, you have 1, otherwise you have 0. So that means the g of t can be written as u5 minus u20. Why is u5 before 5? This is 1, this is 1, this is still 0. And when 5 to 20, this is 1, this is 0. So that will be 1. And after 20, both of them are equal to 1. So the function is still 0. So this is the really function. So the g of t is this u5 minus u10. So this is very typical for any of your exams, is that when you start the exam, the first thing you would like to do is to transform your target function for the right-hand side into a sum or linear combination of unit step functions. Once you have this unit step function, the differential equation is transformed to something like this, right? So let's let me write it somewhere. Okay, so let me write it somewhere. Okay, so right, so the differential equation is now transformed to this equation, Laplace transform of 2y double prime plus y prime plus 2y. Okay, so Laplace transform of 2y double prime plus y prime plus 2 times y is equal to the Laplace transform, remember, u5 of t minus u20 of t, right? So that's what happens to this differential equation. So what's the next step to solve them? Well, you have to remember, you have always to remember that the Laplace transform of y double prime is equal to s squared Laplace transform of y minus s of y of 0 minus y prime of 0. Some people say, how do you remember this? Well, the s is to the power of 1. So in general, you're going to have the Laplace transform of the n's derivative is s to the power of n, Laplace transform, right? Laplace transform of y. And then you're going to say minus s n minus 1 of y of 0 minus s of n minus 2 of y prime of 0 minus dot 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 minus s y of n minus 2, right? So derivative of 0 minus y n minus 1, derivative of 0, right? So let's say n minus 1, derivative of 0. Okay, so just a moment. Why it becomes so big? This is, don't understand what's going on. Okay, just a moment. Just a moment. Okay, so you have this. Okay, so now once you have this, okay, so once you have this, you can see that so this is y of okay, so once you have this, you can see that also the Laplace transform of y prime is equal to s Laplace transform of y minus y of 0, right? So you can always see that the number of derivatives here, okay, so the number of derivatives here and the powers of s, okay, so the powers of s, they should sum up into a finite number, right? So they should sum up into a finite number. Okay, so just a moment. this is kind of, okay, so it's sum up into a finite number. Now you can use the initial conditions there, right? So you can use the initial conditions there. Now once you use the initial conditions, you're going to see that the initial conditions are both equal to 0. So you won't really have any of those terms here, right? So in the end, the left-hand side just tells you 2s squared plus s, right? So plus 2 multiplied by the Laplace transform of y. Is Laplace transform of u functions can be found still on the table. So u5 of t, and so they're going to use line 17. Okay, so you're going to see that it is e power, right? So e power minus 5 times s divided by s minus e power minus 20 times s divided by s. So that's the Laplace transform. So in the end, you get the Laplace transform of y is e power minus 5 times s multiplied by 1 over s multiplied by 2s squared plus s plus 2 minus e power minus 20 times s divided by s multiplied by 2s squared plus s plus 2. So this is kind of typical situation. You can see that we can treat this one as e power minus 5 times s multiplied by capital F of s minus e power minus 20 times s multiplied by capital F of s. So what you want to do is that you would like to transform back. So you want to set a capital. So it is always good to write such a table. Okay, so you have 2s multiplied by s squared plus 2. So this here, I have to change everything a little bit. Okay, so just a moment. Right, so that's here you would like to have 1 over, okay, so you would like to have 1 over the 2s squared plus s plus 2 multiplied by s. So you want to transform back into the function small f of t. And this, to this end, you have to do this heavy business for partial fraction decompositions that I showed you here, right? So that's you have to do partial fraction decomposition, which I'm not going to repeat for today's lecture, but you can do the partial fraction decomposition. And finally, you found your this function by this, remember, whenever you have a denominator, that's a square, you either decompose it or you factorize it into a product of two first order terms. And once you do that, you can inverse Laplace transform, you find your f of t, right? So for this part, I suggest everybody to do a careful research into it. Okay, so you find the f of t, and in the end, remember, once you do this transformation, you have to always shift. So you have to multiply by u5 and u20 for the corresponding functions in order to find the solution. Okay, so that's all. Here today we finished the section on the impulse functions, right? So that's what I want to say.